So suppose you have a 50-liter keg of some liquid, and it initially, for some reason, contains 30 milliliters of green dye. So that should be of. So I'll just fix that right now. Of green dye. Liquid is being removed from the keg at a rate of 20 liters per hour, and pure liquid without the dye is replenishing the liquid at a rate of 20 liters per hour. So the volume of the amount of fluid in the keg isn't changing. 20 liters coming out, 20 liters going in, but the 20 liters coming in does not have any dye. However, you actually manually add dye to the keg at a rate of 3 milliliters per hour. How much dye is in the keg at any time t, where t is given in hours? So we have some container, and we know that there's some stuff going in. There's a rate going in, a rate going out. So if I let d be the amount of dye, what we know is the rate of change of the amount of dye is equal to the rate of dye going in minus the rate of dye going out. The rate of dye going in is pretty easy. It says that we're adding 3 milliliters per hour, so the rate in is 0.003, that's 3 milliliters, minus the rate going out. Well, how much dye is going out? Well, the amount going out is the concentration of the dye, which is the amount of dye divided by 50 liters, times how much is flowing out, and that's 20 liters per hour. So this is the concentration, and this is the flow. Okay, so at the end of the day, this is equal to 0.003 minus 2/5 times d. Write that a little bit nicer. 0.03 minus 2 over 5 times d. So if I rearrange this, I end up with dd by dt is equal to, actually, dd by dt plus 2/5 times d is equal to 0.003. So this is a first order linear differential equation. It's a differential equation because it's an equation with a derivative in it. It's first order because the unknown function d, the derivative of the unknown function d, the highest order of the derivative is 1. And also, it's linear because the only other place that this unknown function d shows up is right here, and it is d to the power of 1. So it's a first order linear differential equation, and so we're going to use an integrating factor to help solve this. So we just have to identify the pieces. So this piece, which is stuck to the unknown function, is called little p of t, and this piece is q of t. So let me go ahead and calculate the integrating factor. The integrating factor is e to the integral of p of t. So this is e to the integral of, what is p? 2/5. And of course, calculate that, it's 2/5 times t. So this is the integrating factor. I'm going to multiply both sides of my differential equation by the integrating factor. So I get e to the 2/5 t dd by dt plus 2/5 e to the 2/5 t times the unknown d is equal to e to the 2/5 t times 0.003. Okay, the reason I multiply everything by an integrating factor is because now the left-hand side becomes a product rule, only kind of in reverse. I repack the product rule, and the left-hand side is actually the derivative of e to the 2/5 t times the unknown function d. The right-hand side, I'll just reorder it here, 0.003 e to the 2/5 times t. And to get rid of that derivative, what I'm going to do is I'm going to antidifferentiate both the left-hand side and the right-hand side. So that gives me e to the 2/5 t times d on the left-hand side. I just undo the derivative there. And then if I take the antiderivative of the the right-hand side, I end up with 5/2 times 0.003 e to the 2/5 t. And then, of course, there's a constant on each side, because each antiderivative comes with a constant, but I'm just going to collect the constants together. I'm going to put them on the right-hand side. I can simplify the right hand side. 5 halves times 0.003 is 0.0075 e to the 2/5 t plus a constant. And now what I'm going to do is to isolate the d, the thing that I'm actually interested in. I'm going to divide both sides by e to the 2/5 t. So this allows me to isolate d. D is equal to 0.0075 plus c e to the negative 2/5 t. Okay, so this is my my function for the amount of dye in the keg at any given time t. However, I don't know what this constant is. I was given initial information that the keg initially contains 30 milliliters of green dye. So when time t equals 0, I'm supposed to have 30 milliliters in there. So plugging t equals 0 into my formula, I have 0.0075 plus e to the power of negative 2/5 t is 0 when e to the power of 0 when t is 0. So that just gives me c. And what I want that to be equal to the 30 milliliters that I was supposed to start with. And so that is 0.03. So with this, I can solve for c. C is equal to 0.03 minus 0.0075, which is equal to 0.0225. Okay, so now that I know what c is, I can now go in and plug that in. So finally, the amount of dye at any given time is equal to 0.0075 plus my constant, 0.0225 times e to the negative 2/5 t, and that's it. So if you give me a time in hours, I can tell you how much dye is still in the keg. And if we actually take a look at this equation, it's kind of interesting to note that as t gets larger and larger and larger and larger, this exponent gets more and more and more negative, which means e to that exponent gets closer and closer and closer to 0. So as t gets bigger, this exponential gets really, 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 really small and effectively wipes out this right-hand side. And so as t gets much, much, much bigger, essentially you're always getting closer to 0.0075 liters of dye.